All right, welcome to the third hour AP Chemistry, and this is Andrew Williams, who's nice enough to record for us today. Andrew, go ahead. Let's see what clowns we have present today. Look at all that.
Yeah, get a good one, Ajay.
Oh, Ajay? Where are you at?
Those iPads are expensive. Don't do that.
Just don't let it crack.
Don't break it. Don't break it. You can break things? Not worth the effort. Ew. Oh, that's not mine.
All right, my friends. May I have your attention, please? We're going to go ahead and start the next chapter on acids and bases. This is chapter number 2 out of 4 equilibrium chapters. So we had a general chapter. Now you're going to see a lot of the things that we did in the last chapter we're using in this one too. Different context, but all the same underlying idea. So I'm not just throwing something totally new at you. The same thing is true for the next couple of chapters too. Keep in mind the reading quiz schedule. We have one tomorrow. That's number 2 because we have one in chapter 13. So we have chapter reading quiz number 2. Whenever's convenient for you, if you can come. Maybe I'll be done. Anyway, just let me know when you're ready. It's fine. So yeah, the next one is tomorrow. The one after that is, the last one is Monday. Monday reading quizzes. Don't forget. Okay.
Last Tuesday was the first quiz of chapter 13.
Yes, it was last Tuesday. Yep. Okay. So we've already talked about acids and bases once this year. Oh, go ahead. Get caught. All right, thank you for that. Chapter 4. That was a long time ago now. We did acids and bases then. You'll say we're going to start with just a review of what they are, how we define them, like what they are. Acids produce hydrogen ions in water. They increase the hydrogen concentration. Bases increase the hydroxide concentration. They either have hydroxide in them and they give it off, or they cause water to get messed up and then it produces hydroxide from water. According to the Arrhenius model, acids have hydrogen and you put them in the water, they give off hydrogen. Bases have hydroxide, you put them in the water, they give off the hydroxide. That's the Arrhenius, the first model for what acids and bases were. Back in chapter 4, we did the stoichiometry of acid-base reactions. This chapter, we're going to get to mostly weak acids and talk about the equilibrium that's involved with weak acids and bases. So Arrhenius has one definition of acids and bases. What's the other one called? Do you remember?
Bronsted-Lowry.
Bronsted-Lowry, right. And who remembers what Bronsted-Lowry, how they define acids and bases? How's that different from Arrhenius? Andrew?
It can be in and out of water, and acids are a proton donor, bases are a proton.
Yeah, that's the big difference there is acids give off hydrogen, or a proton, which is the same as the Arrhenius model, but the bases accept the hydrogen, which is a little bit different. It doesn't quite fit the Arrhenius model for bases. They always work in pairs, and you're exactly right, they don't have to occur in water. These acid bases, this definition has to go into water. But for a Bronsted-Lowry acid base, you don't have to have water. Usually you do, but you don't have to. They can be a gas phase reaction. They always come in pairs, Bronsted and Lowry do. So you have an acid and its conjugate base, or the other way around. Yes?
Should we make sure we know like the acids that you have memorized for?
The strong acids, definitely. You got to know those 6 strong acids. Do you remember any of them? Any of them, Brian? HCl. I heard H2SO4.
HBr.
something HPO.
HCl.
Oh,
Maybe?
H3PO.
No.
H3PO.
HCl.
Not H3PO4.
Oh, I know what you're talking
That's one.
That's quality.
Last one.
Hi, Brett.
It's the nicest acid.
HI.
Hi. Right.
Oh.
Hi.
Yes, memorize those still. Have those memorized. The strong acids. All other acids are weak. All other acids are going to be dealt with ice tables and equilibrium calculations and considerations. And we'll talk about that very soon, like next slide, I think, or the one after that. Yes, there it is. Strong acids, weak acids. We'll get to bases soon, too. I mean, bases are definitely something that we have to talk about. Acids are more common to calculate with and discuss, but bases are there, too, and we need to deal with them. I tried to make this very obvious here with my arrow, and I know I did this back in chapter 4 as well. Acids that are strong, they completely break apart. Do you need me to press that?
Yeah.
Strong acids, they break apart. You get the HA that breaks into these two things. It can't go back that way. So that's why I make the arrow like that. I don't think it goes through the rest of it. Oh, that's a good finish. Okay. So yeah, the strong acids break apart. They don't ever go the other direction. It's always a one-way street. Whereas weak acids, that's not the case. They can go that way and they can turn around and go that way. It's a reversible reaction. This conjugate base can accept a hydrogen ion as it goes back the other way. That conjugate base, there are 6 negative ions that cannot accept a hydrogen. Those are those 6. This other thing down here too. So because weak acids are in equilibrium with their products, we can find a K. And we're always going to call it for an acid, specifically K with a subscript A. Ka is the acid dissociation. Yeah.
Will we eventually run out of strong acid if they can't reform back together? I mean,
Or will you, do they like come together
yeah,
when
is
you,
there a way to make a strong acid?
when you like evaporate the
Yes, yeah. If you take and evaporate the water out of it, like HCl, if you boil HCl, you're going to get the molecule HCl going off as a gas. Yep. Yep. And yeah, they can be made industrially. Like sulfuric acid is, I think, the most produced chemical in the world because of batteries. They make more sulfuric acid than anything. Ammonia is very, very highly produced. But yeah, sulfuric acid. So yeah, these things are produced. They don't necessarily have to occur naturally. Okay. Oh yeah, down here. Weak bases, like ammonia. These are things, make sure you write this part down too. Weak bases are things like amine compounds, organic compounds that have nitrogen in them, that's an amine. And then conjugates of weak acids, like this thing, this A negative. That is a weak acid. And so that can take a hydrogen off of water and it'll increase the pH of a solution. Andrew, make sure you rest your elbows because your arms get tired.
If I move my arms up, you can't really see all of the screen.
So that's
so.
why you gotta
Oh, I
come to
see.
it like this, you gotta put it like that.
What?
Don't listen to him. He's bad at
No,
filming.
Did you have to watch one of
Yes.
Sophal's works?
Wait, wasn't that when we were over in 5th grade?
Yeah.
Yeah, that was
You couldn't see anything.
It was all blurry half the time.
Gosh.
I had to pull up the slides on the other monitor on my computer.
Safawa was laughing at Ajay's jokes the whole hour, probably.
I think Ajay was just like punching him. So he
Oh,
kept-
maybe so. Yeah, yeah. He does that. Distracting. Bullying. So it is a little bit weird that the acids, they only have one reactant. It's just the acid molecule dissociating, breaking apart, so it gives off the hydrogen ion and then whatever's left over. With bases, though, there's an interaction, even in the reactants, with water. The base takes a hydrogen from water and is going to generate those things. So yeah, it is a little bit different looking when you have the two reactants for the base. We'll do lots of those. Okay. Now there are some equilibrium constant K values. I showed you that, I kind of alluded to that on the previous page. This one is very important. Water itself, without having anything done to it, will dissociate a little bit on its own. Dissociate meaning it'll break apart into ions. The water molecule, which is made up of covalent bonds, those bonds once in a while will break and you'll get hydrogen ions and hydroxide ions. So for a few water molecules, they'll just cast off a hydrogen ion. It does happen to a very small extent. The K expression for this reaction, because it's an equilibrium, products over reactants, the water on the left is a liquid, so that doesn't go into the K expression, just like we learned in the last chapter. The K value then is just that times that over 1. And we have found that K expression to give us 1 times 10 to the negative 14. I bet you learned that last year. You remember that from last year? Chem 1? Ellen?
What does KW stand for?
K is just the equilibrium constant, W for water. So this specific reaction gets its own K name. All right, so Kas are where you have a acid dissociating. It's going to be the products over the reactants. Now this reactant will be an aqueous solution, so you'll be able to put that into the denominator.
Did we already do weak acids? Like just. Oh.
Yeah, that's just a K. Yeah. Now weak bases. The weak base has water in its reactants, but the water is a liquid, so that stays out of it. So the Kb, the equilibrium for the bases, are always the two aqueous products divided by the aqueous base reactant. No water in the denominator. Sir?
Well, like, would it not matter because it's water anyways? So, like,
What's one?
the molarity of water.
No, it's actually not one. It's because that's the concentration of water in water. So how many moles per liter of water are there? I don't know. It depends on the density of it.
Like, water density.
Yeah, but there's more than 1 mole of water per liter of water. Like if you have a liter of water, there's way more than 1 mole of it. There's like 55 moles of it. So that would be the concentration of water. You knew that?
No, we're quoting you on it. If like we're ever asked.
55.5 repeating.
Is it really?
Yeah.
So
It's
that's-
1,000 divided by 18. 1,000 is the 1,000 ml divided by the molar mass. Or 1,000, I guess, grams. So divided by the molar Okay, now